Are my slides visible?
Yes, sir.
Yeah. Okay, so let's move on for the live session 2. So we are going to discuss about the problems which you are facing in the week 2, along with um, the week 1 sessions. So first we'll just recap quickly about the week 1, and since the application part we have already covered in week 1, like how the fiber optic sensors works. Then we have also demonstrated the, just a second, give me a second. Yeah, so we have already discussed about the fiber optic sensor, how it works, and what are the types of fiber optic sensors, and based on the modulation, either phase, polarization, frequency. Okay, so today we are just going to have a quick recap of the week live session 1, and after that we'll move towards the live session 2 things, where we'll discuss about the light generation and light detection things. So mostly we'll discuss about the how and what, and um, like how and what we need to have to generate the light, and how we are detecting it. Okay, so let's move on slide by slides. So last class we have discussed about the data science. There the three particular combinations are useful, which is computers, then sensors, and communication. So communication in computers are widely explored, but the sensors, still there are so many sensors which has to be implemented or improved to get the much more efficiency compared to whatever we are having existing one. Their fiber optic sensors are one of the one of the major advantages. So you can understand with this picture, where the generation of the electricity and the distribution of the electricity is done by the smart grid, network, communication network, where all the discussion, like all the team will be having some efforts in using the sensors, like how much distribution of the electricity is been given to the will be given to the factories and households. Okay, then also we have discussed about the different sensors which are implemented, and maybe going to implement in the navigations, like an airplane, and other um, controlling systems. So already we have discussed about the optical sensing, that is very accurate, like sub-wavelength precision, we can go sub-micron wavelength precision. Then optical density of the materials is very sensitive for the strain, temperature, and pressure. And this particular sensing method is non-invasive, or we can say non-destructive, so it doesn't destruct any compound or the environment. It won't interfere so much, so it can destroy that. Also we have discussed about the model. Excuse me, anyone is talking something? Avinash? Okay. Yeah, so there are as I discussed with you, that there are different kind of modulations: phase, frequency, amplitude, and polarization. and it can be changes due to the strain, temperature, pressure and rotation. Okay, then efficient demodulation is a key, because if you are using the source and perturbation in the middle of the source and detector, the problem is you can't get the minute change in the during the perturbation. So you need to use the backscatter mode, where the perturbation, anything is happening in the perturbation. Might be my cursor is not on. Where is that measurement? So anything is happening in the perturbation, it can be detected in the backscatter way. So yeah, then we move towards the why optical sensors are important. Then what are the sensors, what kind of modulation is there. So first we have discussed already about the amplitude modulated sensors, where the gesture recognition is one of the best example, where the array of light of point projected towards the screen through the screen will be detected by the CCD, and it will behave as a gesture recognition. Similarly, the phase modulated sensors, which has been used, which used for the modulation of light. One of the best example is Mach-Zehnder configuration, where the input light will be splitted into two parts, two fibers, and one will be act as a reference, another will be act as a measured one, and you will get the intensity change while you are measuring it. The phase modulated intensity modulated changes can be measured with this. Similarly, the phase modulated sensors can be made with Sagnac interferometer, which is very much useful for the gyroscopes, which is being used by aviation industries like aeroplanes, which is having the accuracy of 10 to the power minus 3 degree per hour, which is quite high. So it can be also used for the the phase shift can be converted to amplitude variation, and it can be used for the very high accuracy measurement of the angle. Similarly, the polarimetric sensors also has been used or being used, where that the polarization will be changed if you are changing the angle, and it will be double. It is the angle is doubling if you are using the response from the backward side. Okay. Then fiber optic current sensor also we have discussed last week, where the induced current generates the changes the polarization, and based on that it can be detected either it is the vertical polarization or horizontal polarization using this polarization beam splitter. It should be like this. Okay, then moving towards the next one, which is very important but unexplored, much more explored in the polarization phase and intensity. But wavelength modulated sensors are very less and very accurate, but the controlling is very difficult, where the perturbation areas can be increased, and after it can be spatial perturbation can be also detected. For that, the fiber core can act as can be used as a Bragg grating, or it can behave like a Bragg grating if we are giving input light in the optical fiber, and that's how it works. The wavelength modulated sensor will move, and we'll discuss about this one a little bit more in a future slide. Here you can see that the perturbation, like for the lambda 1, lambda 2, lambda 3 and up to lambda 5, how it is changing while changing the positions. So the broadband light is uh, propagating towards the circulator, and it is again redirected towards the lambda, like the perturbation area, the sensor side, and the feedback light is circulated towards the OSA, and it is moved to the computer, and you can see that how the wavelength is shifting with the perturbation. So till now we have discussed we have recapped the amplitude, phase and phase, wavelength and polarization modulated sensors. We have not discussed about the distributed fiber sensors. Am I live? Yeah. Okay. So distributed feedback sensing is one of the major um, demands, because it can be used for so many things. Either you can see that it can be used for the bridge, dam and airplanes structural health monitoring. Also it can be used for the exploration in under ocean or inside the downhole to monitor the gas or oil exploration. Okay, so based on the depth, it can give the temperature variation at the particular range. So that's how it works. But there are like two types of distributed sensing using FBGs. So one is quasi, where you can get the information based on the wavelength, but there will be a problem with the if you are seeing the perturbation here and here, in between distance there is no, you can't get the information for that. So to rectify the information, or to rectify the problem, to get the information, the perturbation can be done anywhere if you are using the wavelength temporarily. Just a second. Temporarily if you are detecting temporarily, so you can see here that wavelength will be having very high speed wavelength, high speed pulse laser, which can be detected where is it throughout the time through the optical receiver, and you can get the throughout the length what are the perturbation are happening inside the, like temperature range or something, so that can be sensed easily. Now also it can be easy if you are using the brilliance or the stock and anti-stock shifts, because the relay will take the information, but also the stock and anti-stock ratio with the changing the temperature will have the accuracy compared to the relay and the brilliance, which is in the 4 to 5 order, and it's almost brilliance also almost same, but the inelastic scattering like a Raman will be having the 6 to 7 times lower than the incident level. So which depends on the temperature, which also can be used. So before discussing this phenomena, we'll just discuss about the optical time domain reflectometry, where the laser can be the pulse width, high pulse width, the larger pulse width optical band can be sensed, but the problem will be in the during the detection will be it will perturb both places, like two sensing area. So if you are moving towards the smaller pulse width, so So the problem will be with the intensity, but the result will be accurate. But anyhow, it can be also rectified with the number of times accumulation. Here you can see that OTD are set up where the signal processing unit first sends the signal to driver and it triggers to the laser, where the light pulse propagates to 3 decibel coupler towards the um, testing. So here you can see that how the fibers are connected tip to tip, and that's how the intensity is high. And then after that, in the air, this is in air, then the Brouillon's scattering loss, because of that the intensity is going down. Again you can see here, again here it is increasing, and both places will be having the feedback towards the photodiode, and that will be detected using the ADC. That will be analyzed, that will be amplified and converted to digital signal through ADC. As you can see here, that launch power PL, the power is given in the fiber will be having this way irrespective to the distance, and the backscatter power will diminish with a few kilometers if you are getting the signal. After few kilometers it will be having the problem, because the receiver noise will be having some value, and below that if you are going, then it will not be detected. It will be like a signal to noise ratio will be very poor, and that's why you can't detect here. But it can be enhanced by implementing the accumulation, and based on that the average after averaging the noise level will go down, and that's called the SNIR. And the 2L will be from the backscatter power from 0 to noise level of averaging. Okay, this is the 2L level. Yeah, so these things we have already discussed. Today we are going to discuss about the photodiodes, how it works, and laser diodes, how the source and detectors works. Just give me a few minutes, 1-2 minutes. I'll just bring my notes and I'll write down. We'll go step by step. Okay. Yeah. So just go to the PPT. Sorry guys, it was a little bit problem. Let me check everything is fine. Yeah. So today we are going to discuss about the optical sensors system, where first we'll discuss about what are the parts of the optical sensors. So there are few parts. First thing is optical source. As you know that without optical source, the optical fiber sensors how it will work. So it's too difficult to write with this thing. Okay. So we know that what we are using for the source. Can you just engage and let me know that what are the things we are using as a source for the this kind of systems? What can be used, or you have, if you have recapped this week 2? Did you guys recap this?
LED lasers.
Yeah. So it should be very compact. Yeah. So the compact system we need to use because we are using for sensing application. So basically the semiconductor based LED or laser diode. Other than that, what we need is the center wavelength, how much it should be. So center wavelength can be in the visible region 400 nanometer violet, then 650 red, okay, in IR also 1550 or something like that. Then we need to have one more speciality, that is spectral width. For few sensing application we need large spectral width, okay, and for few it should be very sharp. Okay, very sharp one. So from few nanometer, few hundred nanometers to picometer also. Okay. Then apart from that, you need to have one more feature, that is either you are using for the CW, like the sensing is capable with the CW, or you need to use pulse laser. Okay, then apart from that, the noise, there will be signal to noise ratio. The noise, it can be either relative intrinsic noise, okay, RIN, or it can be phase noise. Okay, apart from that, one more thing is there, that is coherency. So anyhow, if you are using the laser diode, it will be having the spatial and temporal coherence. You can monitor it, either you can or you can change it according to your application. If you want temporal coherence and spatial coherence both, or either. Apart from that, yeah, we need to go for the photo detection system, which is the one of the best example is PIN photodiode or APD, avalanche photodiode. So first thing what we need to check for this, actually there are three things. One of you guys can tell me what are the things we need to check for this? What should be there for the detection? The most important thing, the most important thing is like absorption. Where it is absorbing, in a visible range, or in a IR range, okay, or mid IR range. So silicon is the best photo detector. Silicon based photodiode is the best photo detector for this, and for this indium gallium arsenide. If you know, I think you know already. And then it comes to the responsivity. Okay, so responsivity with, again, the absorption, the wavelength, which wavelength can be which wavelength can respond based on the material. So silicon is visible for visible range as we discussed just now, and for IR, indium gallium arsenide. Then if you are going towards, this can go up to 0.4 to 1. I forgot that, 1.1 micron. Then it will go in above that, okay, easily. Then second thing is bandwidth. How much bandwidth it can cover. The third thing is noise. There will be so many types of noise. What are the noise? Can you just tell me? You guys engage in the discussion. It will be very important for you. You will understand more and you will be remembering for a long time. Might be it will be useful for your examination. Since it is a very basic, we are just discussing about the designing optical sensor designing systems, so it can be useful for you guys. Okay, let me know what kind of noise are there in this. Okay, so moving towards next thing, the noise. So there will be short noise, then there will be thermal noise and dark range noise. Okay, so short noise is it's because of the random arrival of photons. If the photons are arriving randomly, so because of that short noise happens. Then thermal noise because of the thermal because the photodiode, suppose this is a photodiode, each and every place there will be no proper distribution of thermal energy. Once light is hitting, it may generate the um, uh, thermal energy as well, phonons, and it might be having somewhere here more thermal distribution compared to here in this place. So that's why because of that it may generate the thermal noise. Then there will be a dark current. Without photons also sometimes photodiode generates the current. That is because of thermal energy. Thermal energy based excitation. Okay, so it will go from the valence band to conduction band, and that's why sometimes the dark current also we can see. Now I want to ask you guys the to detect the light or to detect the signal using photodiode, what is the essential thing, like your photon energy and the band gap, how it should be correlated? Can you tell me? Your photon energy h nu, it's an incoming photon, you have photodiode. Photodiode is having two things, semiconductors P and N. I am not going for the PN first. And you are hitting it, generating the current. So there will be a band gap. Okay. If you are moving towards outside, then it will be more denser, and vibronic bands and all, electronic bands. Okay, this side it will be denser compared to towards this. So you have EG, EC, EV. Let me know what could be the relation between EG, photon, and EG. Please, anyone? So for the photo detection system, are you guys there? Am I live?
Yes, sir.
Yeah.
Photon energy should match with this energy gap.
Yeah,
And
that's correct. Yeah.
and
So
Avinash is texting in common chat answers.
okay. I am on the PPT. I'm on the PPT. I can't see to both things together. I don't maybe. Yeah. Could you explain FBG? Or you could have asked me directly. Actually, I am on the PowerPoint slide. I need to write there also. So I can't go every time to Google Meet messages. I need to check. Okay, FBG will discuss later. First, we are going to finish this thing. Okay. And after that, I'll come to the FBG. Okay, Avinas. So, photon energy should be larger or equal we can't say, but larger at least we can say, then EG. Then only the photo detector will detect the light. So as we know that there will be like depletion region, everything you know. I think those things I don't need to explain in the detail. You'll be having the just a second. Band gap, and the Fermi energy will be conduction band of E will be hello. Too much. So where were we? Yeah. So we know that Fermi energy level, everything. Then the what we were discussing here. Yeah. So band gap also we know that for silicon it is indirect band gap. For indium gallium arsenide that is direct band gap. Okay. You can see here like this. Indirect here direct. Now what we need to discuss is, as we know that it should be photon energy should be greater than this. How will understand the bandwidth? So there is an equation for that. Intensity versus wavelength. If you have this band, it won't be like this. It will be Gaussian. Then there will be equation 1.8 kBT by h, which is for 11 terahertz at temperature which is approximately 300 Kelvin. Okay, it means like the band gap, if you are calculating the band gap from here to here, the full width half maxima, it will be 80 to 90 nanometer. Wow. And if you are talking about the actually yeah, so if you are talking about the power of laser, how we can calculate, this is for the light source. Okay, so how we can calculate the power? There is an equation for that: intensity by charge into photon energy into eta internal. Okay, internal quantum efficiency and external quantum efficiency also. So internal quantum efficiency, how we will calculate? You must be having the tau divided by tau r plus tau non-relativity. Then external will depend on the refractive index n plus 1 square. Okay, so if you have the structure P and N, which is having heterostructure as well, where the photons are generating. You have electrodes both sides, the contacts. Then the light is leaking out from here, which is very less, and it depends on the eta external. Okay. Otherwise, the light also will propagate, like scatter in this region, which will not effectively come out. But from this, it can be directly come out. For that, this dual heterojunction, dual hetero structure we take to get more high intense laser power or LED light. So to get the lasing, we will use high reflective coating material here, and here partial reflecting material coating. Okay, and we know that the Fabry-Perot cavity effect will happen because of back and forth light propagation, and that's why we are getting the laser diode phenomena, like lasing phenomena, and that's how the laser diode works. Also, the output power of this depends on h nu by q, I internal, I minus I threshold, eta external. So we have discussed about the these things for the LED also. Only the thing is, here beyond threshold only the light will be light will come out from the diode, and that is the amplified one. So stimulated emission will be act as a lasing, and this eta external will behave like which is alpha m divided by alpha r, which is the loss from this side. Alpha loss is from mirror side, and this side is reflective coated. So this is alpha r loss, and this is having alpha m loss. Okay, so this is depends on this particular parameter also, the power, how much output will come. Also, if you plot power output versus voltage current, so power output versus intensity, so it will be having the normal increment initially, and then suddenly it will be having the sharp slope. Okay, so this is because of the spontaneous emission, and this is because of the stimulated emission. Okay, then as we are discussing about those things, let's move to the next thing. So we have discussed about the laser diode, and also I told you that usually we take the PIN. Why we are taking the PIN instead of PN? Because the increasing in the deflection region. Can you tell me in the comment section why we are using the I instead of the PN directly? Why it is good compared to this one? For reason I'm checking comments also. Can you type? Why PIN is important, and why why the eye, the deflection is very important compared to the directly using PN junction. Anyone? Please type also. I'm seeing the chatting also. Larger deflection for more E and HPA generation. Yes, correct. Nice. So, but there is one problem also. What could be the problem because of these things? Will it be having a problem? Okay, why it is not coming? Yeah. So more number of electrons and hole pair. Okay. Hole generation. Now we will go for the optical receiver things and we'll discuss about those things. If you have doubts, you can text on the meet chat. I'll check meeting chat. So moving towards the optical receiver, which is very important for the detection system. Please let me know what are you able to understand what I'm saying? So we are moving towards the optical receiver system where we will discuss about the first how the photons will be generated, like used to generate the current, and the small current will be amplified or converted into a voltage, and it can be decoded with the ADC. It will be converted in digital form. So for that, first thing is like we need to have the absorption system where the photon will be absorbed and converted into current, which is a photodiode PD. Okay. I need to make it more better to understand. You must be having the photodiode, which will generate a current I, P, H. Then it will go to the TIA, where it will be converted to voltage, which will be again amplified. Okay. So you will get amplified, voltage amplified, and it will go to the ADC system where it will be converted to digitalized form, and it can be detected, or it can be since it can be converted into the digital form, which can be seen on the computer screen or wherever we are sensing based on that. We can have the application for that. So how it works actually, the same thing is happening here also, but there is one advantage is or one important role if you are using a semiconductor material, which once the light is hitting here, it will generate the holes and electrons. Okay, you can see here easily, it will be having the electrons and holes generation, and that is being, it will travel, and because of that there will be a current, it will produce a current IP, and which will be used for the voltage generation, and after that it will be improved further. But in this system there is one problem, which is once we are using multiple TIAs and amplifiers, it will also increase the noise. So noise compared to signal will be having some problem. So how we can rectify it? It can be rectified either by having a deflection region, okay, and also more accumulation. That is the one of the thing, accumulation also important. Now I want to ask you that if you have what you can say, yeah, so you should get the temporal response in a square waveform, where once the light hits, it should be on the high state, or it should produce the current immediately, and once the light turned off or is detecting off, turning off the detector, then it should be turning off the light source, it should go immediately to the lower current region. So with the time, respective time, usually what happens with the PN and PIN, what we are seeing is it will be like nicely increase, and after that it will be having some this kind of region. Might be, I just make some mistake here. It will be like this something. This is because of what? Can you tell me? Because of what why you are getting this kind of slopey response with respect to time? Type in chat box also, it's okay for me. Like this something. Let me check chat box. Guys, type what is the reason. Okay, delay in response, and why it is happening actually. Yeah, delay in response, okay, but why it is happening in PN photodiode? What is happening? So it's delaying. So response usually depends on few things. One is the drift velocity. So if you consider velocity versus electric field, plot, we can see that at a zero electric field also there will be few like some velocity of the both electrons and electrons and hole pair will be having some velocity. If you are increasing the electric field, it will go slopey way and suddenly it will be having some kind of constant. If you are increasing the electric field also, it will not change the velocity. That's called a drift velocity. And which can be up to 10 to the power 5 meter per second, and this is called diffusion velocity. Now if you see response 3 dB, it depends on the what response at lower frequency. What could be parameters for that? First thing is 1 by 2 pi time, which is dr and also rc. So first thing is the travel time, that the ions or the both electrons and holes both are traveling. So if you increase the travel time, how you can increase? You can in generation and increment of the electrons and holes can be done by implementing the deflection region and incorporating the deflection region inside the PN photodiode, incorporation of the I region in the PIN photodiode. So there you can see it will be having negative charge, it will be having positive charge, and this is the drift region where this is where the electrons and holes both are drifting, dr velocity with velocity of dr, and the width is approximately w. So this time is directly like it's correlated with the width and drift velocity, which is w by dr, vdr. Okay, so w is the width of the region, deflection region and depletion region, and vdr is a drift velocity. Similarly, for this there is this is directly related to the capacitance, which is equal to epsilon a is area and w is the width. As you can see here, the w is both sides, it's having the like in the both it is having some impact, and which can be also makes some contribution to the response. So if you are increasing W, then the denominator will increase, and that's why the response time will increase. But if you are increasing the W, increasing the W, this capacitance value will increase, and that's why it is having it is making some changes. Okay, so there is a contribution both side in both side. So you can't change this parameter, or you need to increase the W to get the larger response value. But if you are increasing it, it is also increasing the capacitance, which is capacitance is directly proportional to the area, and that's how the capacitance can be reduced by reducing the area. So capacitance also will be reduced, and that's how the response time can be increased. Understood? Am I clear?
Okay, sir.
Yeah. Nice. So response excuse me, response we have discussed already. We'll go for the responsivity. Which is directly proportional or directly correlated with the photocurrent. And if we photocurrent per unit power, so optical power. So how it could be related? So photocurrent IP, whatever is generating, and power input, whatever has been given. So it will be in ampere per watt. Okay. And okay, just a second. So we'll go for that exponential things also. So first the current, photocurrent, and P input, optical power, that is the responsivity. And then we need to discuss about the photocurrent, how and what, where it will be correlated. So photocurrent is depends on the P input divided by photon energy. One minus RF. RF is the this is the reflection which is happening through because of the photodiode or PD's region. Okay, we'll discuss about these things also. Just a second. PINN. First thing, this will clear about these things, why the reflectivity is coming here in the picture. Once the light is, the photons are approaching to the photodiode is having the refractive index is approximately 3. Refractive index is approximately 3, while for air it is 1. So what will happen if you are using the high power light and detecting it? So what will happen, that because of the absorption most of the light will reflect, during the small light will propagate. Okay, and that's why look, sorry, what I was saying that because of this contrast, refractive index contrast, it will be having the problem with the reflectivity, and after remaining from 1, after subtracting the reflectivity from 1, whatever the light is falling on the photodiode will be converted into the current, will be contributed into current. Then there will be a photoelectron conversion efficiency. So photoelectron conversion efficiency also depends on the photodiode's material. This is the intrinsic material of the photodiode. Suppose you are taking a silicon photodiode. For that, because it's an indirect band gap, so it will be having the efficiency of 0.7, while indium gallium arsenide, which is having the direct band gap, will be having the responsivity, the photoelectron efficiency, conversion efficiency 0.9. It is clear? Is it clear? Okay. If you are moving towards next step, we will be discussing about the one more parameter, which is loss 1 minus e to the power minus alpha w. What does it mean? This alpha, like loss, is depends on the light, how much it is propagating through the photodiode. So it will be having the exponential decay, e to the power minus alpha x. Okay, and that's how this is also one of the how much light is decaying, which we need to this loss we need to subtract from 1, and the final equation will come like this for the photocurrent. Okay, so there is one question here, because again it's a width, again coming the width. So please tell me, if you are increasing the width and decreasing the width, what will be the effect on the photocurrent and the bandwidth of the photodiode? Please tell me. Can you please write on the chat box also, if it is possible? So photocurrent is we have derived the equation. Then you need to just tell me that how it is, the width is correlating with the IP and bandwidth. As we discussed with you previously, one more thing, the response time. I'll just draw here. It should be like this, the square wave, but delay in response, because of that you will get such kind of curve. And if you are using PIN, then might be you will get almost normal curve. Okay, can you tell? Answer it. Increasing bandwidth, decreasing current. I didn't understood. Increasing with width or decreasing with width? Avinash? If width is increasing, you are saying that bandwidth will increase. and current will decrease, or it is vice versa? There are two conditions, no? First condition is this. Second is this. So first you tell me first one, then automatically the second will come up. Please, anyone? Hurry up guys, we need to go so much. After this we have to discuss about avalanche photodiode, and that's the final. It will take 10 to 15 minutes. So if you are not sure, I will tell you, increasing in the width will decrease the photocurrent and increase the bandwidth. But sorry, I told wrong. Increase the photocurrent and decrease the bandwidth, and the vice versa is also true. So what is happening here is, once you are increasing the width, the loss will be more, but the yeah. So it depends on the width directly. It's proportional to the photocurrent, but it also decreases the bandwidth. So that's why the PIN photodiode will be having some certain limitation of to increase the width. They can't just increase to get the photocurrent. Either they can get the photocurrent more, bandwidth will decrease, and if they are decreasing the width, the current value will decrease, and that's why the bandwidth can increase, but the current will decrease drastically. Okay. Then responsivity, again we can derive as a Q eta h nu, which is again in ampere per watt. Also it can be written like n lambda by 1.24, which is one of the quickest way to correlate with the wavelength. Okay, instead of frequency we can go for the wavelength, and it can be easily correlated. Also there is some problem with the responsivity. What is that? Is if you are plotting responsivity with lambda, ideally it should start from 0 and it should go linearly. But what happens? It goes and has some certain value. After that the responsivity decreases. Okay, it's called cutoff. So why it is happening? Can you tell what is the problem with this? Why it is responsivity decreases after some time, after increasing the wavelength? Longer wavelength it will not survive. The responsivity will not be there for few photodiodes, and based on the range. So what could be the reason? Anyone please? Avinash, Janani, John. Please tell me what could be the reason here. Are you following what I am saying? The responsivity decreases drastically after some time, after some wavelength. Why it is happening so? Response. Because as Janani also told, what is that? Photon energy should be greater than. Anything happened? Okay. Should be greater than the band gap. Hmm? What I'm saying. Okay, and that's why after the once the if you are going like this, after certain band gap it can't be detected with the photodiode because the absorption won't be there, certain value should be there. But why it is not responding after some value in the shorter wavelength, when once it is going, suppose for silicon, as I mentioned previously, it can go from 400 nanometer to 1100 nanometer effectively. Now you can understand that 1100 nanometer what is happening, because the photon energy is too less to compare to the band gap. But what is happening with this area, 0.4 micron? Anyone? Yeah, mismatch in the photon energy and band gap. Yeah, correct. What about the high energy? Photons are having so high energy, but what is the reason why it is not responding properly? Now at 400 micron, 400 nanometer, the photon energy is way high. Here it is low. So what's the problem here? Why it is not going for 300 nanometer also? 0.3 micron. Anyone? The reason is, once the photon energy is way high, okay, it will be having the problem with the absorption. If you have the photon energy is way high, the most of the light will absorb this area, then it will go slowly towards the other region, like it will be spreaded slowly, and it will be having like faded, the photons won't reach up to the full depth, and that's why the absorption won't happen properly, and the responsivity decreases drastically. Understood? Able to follow what I am saying? Okay. For suppose you are taking indium gallium arsenide, then what will happen? It will start from 0.8 micron, okay, and it will go up to some 1.7 micron, and there it will stop working after that because of the cutoff, wavelength cutoff. Photon energy is lesser than the band length. but here also same thing is happening. The power will be drastically decreased because it will not be having any because of the absorption, high absorption, it will not propagate through the path, and that's why the current won't be produced and responsivity decreases drastically. Okay, so larger the absorption, smaller the penetration depth, and low responsivity. Okay. Moving towards the avalanche photodiode, where we'll discuss about the first thing to understand the APD is understanding actually what is the avalanche photodiode. Anyone can tell? Have you seen any time, or have you saw like mismatching photo? The last comment is at 7:30, 7:36. Nobody commented. Why? Chat it. Something you guys chat. I'm asking about the avalanche photodiode. Have you seen any time, or have you heard about it? Or how it works? At least yes or no you can tell.
Yes, sir.
Yeah. So there will be a phenomena called impact ionization. Alpha. So what is the impact ionization alpha? It is like if you are giving so much electric field, the electron will drift, and it will due to the collision, it will generate again electron and hole pair, and the same thing will be done by this. It does again generation of the electron and hole pair. Okay, so there is like a chain reaction. Electrons will hit to the electron, generates the hole and electron again it will go for the next one. This is the process it happens. Okay, and if you see the impact ionization plot versus the electric field, and for that we need very high electric field, 10 to the power 5 volt per centimeter, which is way high to destroy few compound also, that much high electric field. 0 1 I'm keeping in the value in 0 1 2 3 4, so multiplied by 10 to the power 5. This side is the 1, 10 to the power 3, 10 to the power 6. So if you see for the silicon, it will be having the indium gallium arsenide, it will having this kind of flow. Okay, and for electron, and this is for hole. While for silicon it will be like this. Almost it will start from 2 something and it will go. Similarly for hole, as you can see, indium gallium arsenide, the field is required less come to get the impact ionization compared to the silicon. Okay, what is happening in this, why it is so, because we'll discuss about this one later. First we'll discuss about the energy distribution in the this range. Okay, so instead of the pi junction we are using one more into the depression region. Towards the n side we'll introduce another p region, and what will happen with this, it will be having this region, then this region. Okay, so if you see the energy electric field distribution, it will be slowly increase, then it should go down, but it will not go, it will follow the trend, and here suddenly again it will jump and it will make a sharp jump and it will come back. Okay, so here if it is something is going beyond this, we'll be having the impact ionization. Impact ionization of electrons. So this is required to have this energy is required to have impact ionization, which can be also determined by this way: dE divided by dx, which is directly proportional, it's related to impact ionization of E and current, electron current, plus alpha hole H, right, IH. Okay, similarly for hole also same thing, minus H dx dE dHIH. Now the ratio of impact ionization Ka will be alpha n alpha H, and alpha E. For silicon, this Ka is way lesser. Okay, so how it is correlating with the gain? So we have the gain. Gain is m, the multiplicative gain, which is proportional, which is equal to 1 minus Ka divided by exponential of minus 1 minus Ka dot K dot alpha E Wm bracket minus Ka. As you can see here, there will be two conditions for this APD. One is if we'll move to the next one and write here again same equation, 1 minus Ka divided by exponential if you plot m versus phi Wn dot Vb So for Ka is equal to 0, it will be having this kind of a slope. Then if you are using the second, I need to write the values 0, 1, 10, 100, 2, 3, 4, 5. Then if you are going for the Ka is equal to, maybe here that Ka is equal to 1, then the value will go in this way. Okay. This is, and if Ka is equal to 0.1, then value will go somewhere like this. The slope will go like this part. And if Ka is equal to 0.5, which will go like this, where you can understand that this is the example for indium gallium arsenide. Are you understanding? So the multiplicative gain is directly depends on the impact ionization ratio, which is alpha H upon alpha E, and which can be also this ionization impact of electrons will be generated if you have this kind of region above this region, otherwise it won't be, it will not generate. And second thing, you need for indium gallium arsenide you need lesser power to generate the to act as a APD, but while for silicon it requires more electric field. So here we'll stop today, and we'll discuss about few more questions if you have doubts you have related to the assignments or related to the course. Avinash was asking about the FBG. Let's move to that and let him ask what about the, can you explain FBG? So what do you want to know actually FBG? Just yeah, please tell me what do you want to know actually?
Next slide, yes, this one.
This one, yeah. This one?
Previous one. Previous one. Yes, this one.
Yeah. What is the problem? What is the doubt?
These black colors are. What are these black colors in the picture?
You are talking about these things?
Yes.
Yeah. This is like a fiber. The core, when the wavelength, like it's acting as a what you can say, when the perturbation happens, it will generate what we can say, that phonons, and that's why it will be having the Bragg scattering. It will generate the Bragg scattering because of the stocks and anti-stocks Raman scattering, and because of that you will be having the temporal Bragg grating generation. And you can see here, this area will be, you can see here also this what is happening. So you will be having the refractive index change, slight change in the same core if you are having that kind of phenomena. So what's your question actually?
Like
How it is generating,
like
or
are they? Are they light effects or the material effects?
Yeah, material effect, but with the interaction with the light. It's a light matter interaction. If if you propagate the light, it will generate the phonons, and the phonons, if it is localized few areas like these black areas, it will change the refractive index of that particular area.
So,
Understand?
regular change of refractive index of the fiber material,
It's not regular change. It's a it's a it's a temporal change.
like alternate black.
Alternate, yeah, yes. So it will be having the refractive index low high. Those that kind of pattern will be there. That's what the temporal drag grating it will affect. It will act like a drag grating. Are you understanding what I'm
It's
saying?
written narrow band. It's written narrow band filters with sharp roll off.
Yeah. So
I didn't get this.
yeah. So what will happen? Like you will be having the refractive index change. It's like a birefringing material. Then few wavelengths will be once the input light is given to the it's propagating through the core, and it will act as a Bragg gratings because of I told you the because of the refractive index change, because of phonon generation, and because of that the light will be having some sharp like you are sending some signal which is like this band, okay, or laser, maybe very sharp laser, but anyhow it will be having some bandwidth, and suppose you are propagating and one of the wavelength is missing from that, so it will act as a filter, narrowband filter, so it will be having the lambda, that lambda will be missed and that will be propagated back because of this Bragg's grating effect. Are you understanding what I'm saying?
Yes, sir, yes.
It will act as a narrowband filter where one particular wavelength or few particular wavelengths will be filtered out and it will be sent back to the source side, which can be detected easily
So,
with this kind of setup.
so finally, it will act as a narrow band filter.
Yeah, narrowband filter.
Narrow
Yes.
band filter.
Yes, yes. Your doubt is clear now?
Yes, sir, yes.
Okay. You can go through once more for lecture. That is discussed very nicely by professor. Okay. Anything else you want, guys? Any other doubts? The for week 2 also you can discuss if you have any doubts. Because the problem is almost it took so much time to explain. Might be I should reduce this and I should increase the question answer session more. Maybe it can be useful. Okay. Maybe, yeah, can I ask few questions to you guys if you are interested? Maybe you can discuss about the drift velocity, like how and why the drift velocity can't go up after a certain level. What could be the reason? Anyone please tell? You have drift velocity for a photodiode, suppose we are using pairs, electron and hole pairs will be having some particular drift velocity. Sorry, I'm somewhere else. Yeah, this one. Maybe here and right. You have velocity meter per second and here electric field. So why it is like this, and suddenly it's having the like not like this. Almost it's 10 to the power 5 meter per second. Why it is not increasing the velocity if you are giving more electric field also? What could be the reason?
Because of area limitations.
What limitation?
PM.
PN limitation.
Space area limitations.
Can you type? It's better. Not able to. Mismatching photon energy. This is the last one. Avinash, can you tell? John also there. Just discuss something. After that we'll finish it off. We have more 5 minutes. Then I'll ask you one question. You need to solve it and answer it. Spatial limitation. Okay. Then okay. Okay, let me ask one question to you. Calculate the responsivity if you have the lambda value of 1.35 micron, then efficiency which is 0.9. Calculate R. What could be the R? So a very simple question I have asked. Anyone please tell? Anything? There is one let's write the formula. R is equal to lambda divided by eta lambda divided by what is that? Yeah, 1.24. Now we calculate. Should be 0.98 micron. Right? Hmm? 0.98 approximately. What is the unit? Micron. micrometer. It's not in micrometer. Responsivity will be in ampere per watt. Okay, you are so close. Okay, then we'll wind up today's session. Then next one we'll discuss more questions. I think today's theory is too much. How you feel actually? Can you just let me know? Theory is more, or we should have some more questions, or is it is okay to go like this?
Session recap is good to understand, sir. Also, question answer explanation will also.
Yeah, question answer and
We need both.
Okay, then I'll take a feedback and I'll proceed for that. Maybe I'll recap, and after that quickly I'll just finish it off for the questions. Because recapping is useful, because most of the students will not go and watch lecture properly. That's why they will be having so many doubts. Okay then. Okay guys. Let's meet on next Saturday. Okay, you can leave the group. You can leave the meeting now. John, you have any doubts?
No doubt.
Okay then. We'll meet next week then. Okay?
Okay.